Today's lesson is 5.4 in your textbook. It's on the medians of triangles and the altitudes of triangles. Let's start by defining what concurrent lines are. Concurrent lines are three or more lines that meet at one point. The point where they meet is called the point of concurrency. And here's a drawing of it. So right there you can see those three lines all meet at point P right there. So there's point P. That is the point of concurrency. Okay. Now a median is a segment that has the end point at one vertex, at one corner of the triangle, and the midpoint of the opposite side. So for example, there are the three medians of the triangle. You can see each of those red lines starts at the vertex of one of the vertex of the triangles, and then goes to the midpoint of the opposite side. The centroid is the point of concurrency of the medians of a triangle. So in that drawing that I drew, there is the centroid right there. That is the centroid because that's where all the medians of the triangle meet. And what we know about medians and the point of concurrency of medians is the following: that the point of from the vertex to the centroid is 2/3 as big as the entire median. So EC there, from E the vertex to C the centroid, is 2/3 as big as the entire median EG. Just like DC, from the vertex D to the centroid C, is 2/3 as big as DJ, and FC is 2/3 as big as FC. So putting this all into English, the medians of a triangle are concurrent at the point which is called the centroid of the triangle. That is 2/3 the distance from each vertex to the midpoint of the opposite side. And for any triangle, the centroid is always inside the triangle. Now that we know all that information, we can actually do some problems. So here's an example of a problem. In the diagram to the right, ZA equals 9. What is the length of ZC? Well, we see that ZA is that point, A is my centroid and Z is my vertex of the triangle. So ZA is going to be 2/3 as big as ZC. So ZA is going to be 2/3 as big as ZC. Now we can just put in the values that we know. ZA is 9. So ZA, which is 9, equals 2/3 of ZC. I want to find ZC alone, so I need to multiply by 3/2. That will cancel the 2/3 and get ZC alone. But of course I can't just multiply the right hand side by 3/2. I have to multiply the left side by 3/2 as well. So when I do that, on the left side I get 27/2. ZC gets the 2/3 and the 3/2 cancel out to get ZC alone, and of course 27/2 is the same thing as 13.5. So I know that ZC is 13.5. That's it for the medians and centroid. Now let's talk about the altitude of a triangle. The altitude of a triangle is essentially how tall the triangle is, and to find that out, it's the perpendicular segment from vertex of a triangle to the line containing the opposite side. Okay. And so for example, it can be inside the triangle, so right there is the altitude. It goes from that top vertex to the opposite side, and it's perpendicular. The altitude can be on the triangle. If it's a right triangle like this, then the altitude is actually one side of the triangle. And if it's an obtuse triangle like the one on the right, it can actually be outside the triangle, looking like this. You have to extend the base out, in this case to the right, and then you can see how the altitude starts the vertex and then is perpendicular to the line containing the opposite side. And just like the centroid for medians, that were always concurrent, altitudes are also always concurrent. So lines that contain the altitude of a triangle are concurrent. And so here's an example of that. If there's an acute triangle, there you can see the three altitudes of that triangle, and in that example it would be inside the triangle. If it's a right triangle, it's actually the altitudes are going to meet actually at one of the vertexes, the vertex with a right angle, so it's going to be on the triangle. And if it is an obtuse triangle, you can see right there that they are going to actually be outside the triangle. So the orthocenter can meet, the orthocenter, which is the point of concurrency that contains the altitudes of the triangle, it can be inside the triangle, for example, like this one with an acute triangle. It can be on the triangle, for example, like this one, which is on that vertex, or it can be outside the triangle, for example, in this example with this obtuse triangle. Okay, so now we know what altitudes are and what the orthocenter is. And so we can go through quickly and explain. So for this one, what are each of these different segments? So AD, when I look at AD, it goes from the triangle vertex, point A there, to a midpoint on the opposite side. That's point D. So something that goes from the vertex to the midpoint of the opposite side is a median. When I look at EG, EG is not perpendicular, and it doesn't have an endpoint as a vertex, so it's actually neither an altitude or a median. Finally, when I look at CF, CF is perpendicular to AB, and C is the vertex. So put that together, and CF is the altitude, or is an altitude of that triangle. Finally, let's actually find the coordinates of an orthocenter of a triangle. So I have a triangle ABC that has vertices at these 3 points. A is 1, 3, B is 2, 7, and C is 6, 3. So that's what I know. What I need is the intersection point of the triangle's altitudes, again, which is called the orthocenter. And so my plan is to write the equations of the lines that contain 2 of the altitudes and then solve the systems of equations. So I need to find an equation for the altitude of a triangle. So let's find the altitude that starts at C and is perpendicular to AB. So to do that, I'd first have to find the slope of AB, and I do that by using my formula rise over run. So in this case, if I want to find the slope of AB, I can just plug in the points A and of AB into that equation there, and I get this here. And because you can see that B has the points 7 and 2, and A has the points 3 and 1. So for 3 and 1 for Y, and 1 for X, and B has 7 for Y and 2 for X. So when I plug those in, I get 4 over 1, or 4. So I know the actual slope of AB is 4. But what I want is the slope of the line that is perpendicular to AB. And that would be the opposite reciprocal of that slope, because 2 slopes that are perpendicular are opposite reciprocals. Or if you multiply them, their product is -1. So the opposite reciprocal of 4 is -1/4. So now I know that the slope of this line of my altitude is -1/4, and it goes through point C. So I'm going to put it in the point slope format. I know the slope is the opposite reciprocal, and it goes through point C. So there's my point slope format, and I can just plug in my values. Again, M is -1/4, Y1 is going to be 3, and X1 is going to be 6. So now I have an equation for the altitude that starts at C and is perpendicular to AB. Now I need to do the same thing again. I'll do it to BC, the altitude that starts at A and is perpendicular through BC. So to get BC's slope, again, I use the same formula, plug in my values, and I get that the slope of BC is -1. So the opposite reciprocal is just going to be -1 over -1, which just equals 1. So the opposite reciprocal is just going to be 1. So now I'm going to use my point slope format, using 1 as my slope and going through point A. So put it in that formula, and my A is 1, 3, so it's going to be y minus 3 equals x minus 1. So now I have two equations for the altitudes. The one in red up here, y minus 3 equals negative 1/4 x minus 6, and the other one, y minus 3 equals x minus 1. So let's put those two equations out over here so we have some more space. Now notice on the left-hand side of the equation, both of them have y minus 3. And so those must be equal. Y minus 3 equals y minus 3. So I can take the two right-hand parts of the equation and set them equal to each other. Now I have that fraction, negative 1/4. I don't like fractions, so let's get rid of it. I'm going to multiply the whole equation by negative 4. So on the left-hand side of the equation, negative 4 times negative 1/4, that cancels, so I just have x minus 6. And on the right-hand side of the equation, I have negative 4 times x minus 1. So when I distribute that negative 4, it becomes x minus 6 equals negative 4x plus 4. If I add 4 to both sides and add 6 to both sides, I get 5x equals 10, or x equals 2. Now that I have x equals 2, I can take either one of those lines. I'll take the one in blue. I could have taken the other one, doesn't matter. And plug in my value of 2. So in this case, it's going to be y minus 3 equals 2 minus 1, or equals 1. Add 3 to both sides, and I've got y equals 4. So if I'm trying to find a point where x equals 2 and y equals 4, that point is going to be 2, 4.